Hello and welcome to the new derivative series through the algebra lens. The purpose of this video lecture 10-minute YouTube type thing is to derive an explanation for why calculus is not as scary as it sounds, and if you don't think that it sounds scary, good for you, really. But for the rest of you who do think that it sounds scary, this is like derivatives in a nutshell. But in order to talk about derivatives, we need to talk about calculus. And if you notice the bouncing calculus, thank you. I spent like 5 minutes of my life on that. Please give me credit. Anyway, it aims to solve two problems. What is the slope of a function, fx, at some x, and what is the area under the curve of fx from one x to another x? Derivatives aim to solve problem 1, and integrals aim to solve problem 2. But integrals are not the topic of this, so we're gonna hastily skip those. Let's talk more about problem 1. I made a little diagram here, so basically what it's trying to say is, what is the slope of this blue line, which is tangent to f of x at x equals a? This is the definition of the derivative, and, it looks complicated. It has a limit in there. What's a limit? Isn't that calculus? Don't we need to learn limits first? Yes, but I'll sum it up very quickly here, because this video is meant to be 15 minutes or something, and doesn't really have time for an in-depth explanation. But basically, h gets infinitely close to 0, but never reaches 0. So h in the denominator doesn't lead to catastrophe, and x plus h is barely bigger than x. So basically, we're taking the slope between these 2 points, but this diagram was made in Paint, and Paint doesn't allow you to create two infinitely close points. So just assume that the points are practically on top of each other, and now we're going to want to take the slope of that to get the instantaneous slope. So, this jumbled mess inside the limit is basically rise over run, what we all learned in algebra. Okay, finally. Back to computation. So finally we can move on from this pesky definition. What is the derivative of something simple? I don't know, x to the n. Well, we could prove what the derivative of x to the n is using this, but how about we don't? As hard as it is to say, we'll just say it's an axiom, even though it's totally not. But we'll just say that the derivative of x to the n equals n times x to n minus 1. Let's do some examples with this. I was very kind to copy and paste, yes, 2 seconds of my life. Control-C, Control-V. The formula up at the top for our first example. And I'm going to let you solve this, or rather plug it into the formula for a second, while I don't know, sit back in my chair or something. And if you don't want to answer it, answer coming in 3, 2, 1. How I would do this, yes, more Microsoft Paint, I know, it's a little bit messed up, but we're making do with what we have, okay? Basically, the gist behind it is move the exponent into the coefficients, therefore you have 5x to the 5th. But we can't just spawn matter out of air, so we need to get rid of one of the exponents. At least that's how I sort of think of it. And therefore, the slope of x to the 5th at some x is 5x to the 4th. Now, if you haven't tried the example for real this time, you need to try. What is the derivative of 2 times x to the 4th? Ooh, looks a little scary. There's a coefficient of 2 now, but it is in essence the same thing. What am I doing? Alright, time's up. If you could pause the video. And, yeah. Anyway, you're going to want to move the exponents into the coefficients, but we can't just have the exponents magically make coefficients appear, so we need to get rid of one of the exponents, meaning that the slope of 2x to the fourth at sum x is 8x cubed. Now, let's talk about the linearity of derivatives. They play nice with addition, meaning we can separate large polynomials, like on the first bullet point, into its constituent parts. Now, we know how to compute the constituent parts, except for 2. What is 2? Like as the second bullet point says, why is the derivative of a constant 0? Well, I drew another little diagram on the right. We can move the exponents into the coefficients, but we can't just magically have it appear. So we make the exponents go down 1, but it doesn't matter because the coefficient is 0. So the derivative of some constant c is 0. And remember, x to 0 is 1, so c times x to 0 is the same as c. Therefore, the derivative of this polynomial is 8x plus 5 plus 0, or 8x plus 5. Now we have some funky derivatives. Hopefully you know trig, because the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of the natural log is 1 over x, and the derivative of e to the x is itself. Very fascinating, I know. Yeah, these are special functions, and you need the formal definition to prove it, but that's like, not in this video. And also, no, you can't use like the examples as before to differentiate e to the x, because exponentials, are special. Alright, let's talk about a few rules. Yes, now we have 2 functions. Woo! What if you want to take the derivative of 2 functions being multiplied by each other? Well, it's not quite as simple as derivative of f times derivative of g. It's actually derivative of f times normal g plus normal f times derivative g. The quotient rule is like the same thing, but with subtraction and a g squared in the numerator. Proven by the definition, once again, not using that. The chain rule is what happens if you want to take the derivative of a composite function. This is probably the most complicated derivative rule that we're going to have. And finally, inverse function rule. Why do I say dgx right here? Because, I was fiddling around with this in PowerPoint, and I just can't get it correctly for some reason, so I gave up, had to use the other Leibniz notation. But yeah, the derivative of an inverse function is equal to 1 over the derivative of the normal function, with x being the derivative of the function a. Why did I say a? X. Yes. So, yeah. With these rules, you should be able to differentiate practically any nice function. So let's have some examples with all of these. Oh, well, okay. Probably need to inform you with the problem-solving strategy that we're going to use. First, we need to identify the derivative rule in this slide that we need. Second, we're going to identify the functions. Third, we're going to plug the functions into said derivative rule. And if we need it, we can use funky derivatives to compute, the derivative of sine or something. So, Let's work with the product rule first. What is the derivative of sine x times cosine x? Well, let's identify the functions. Fx equals sine x, gx equals cosine x. We can clearly see that we're trying to take the derivative of fg. So we use the product rule, we plug it in, and we will use the funky derivatives as needed. Therefore, the final answer is cosine squared x minus sine squared x. Pretty complicated, but we'll get the hang of it. All right, now you try. What about the derivative of sine x cosine x? Now, this is a way of me actually like forcing you to differentiate yourself, because no, there's not an answer for it. So, if you want to check your answers after you watch the video, the answer will probably be in the description or something, whatever YouTube dooley dings there are. But yeah, we'll move on to the chain rule. So yeah, as you can probably tell, the title of the slide is the chain rule, so we're probably gonna use the chain rule, but let's think about it. Is there a composite function here? Technically, there is. Cosine x to the fifth is like a to the fifth, but a equals cosine x. So fx would be the outside function, which is x to the fifth, and the inside function is gx, which is cosine x. So plugging into the chain rule, we're going to get the derivative of this is negative 5 cosine x to the fourth sine x. Pretty complicated. Alright, and lastly, the inverse, oh my gosh, alert. Whoa, what? Whoa, we can differentiate the pesky exponentials. That's pretty cool. And it changes color. Okay. Now, inverse function rule. Let's take the derivative of the inverse of sine. Well, identify the function, fx equals sine x, plug it into the inverse function rule. The derivative of fx is cosine x, and plugging it into the formula, the answer is 1 over cosine of sine negative 1x. Now, when Fluffy Cloud was checking the answers with his little derivative calculator, yes, luckily those exist, it was actually the second bullet points, but then I was reminded, aha, trigonometry rules. We can actually use those rules to simplify a bit. And that's about it for computation. Next video, we're going to get into the applications of the derivative, like, I don't know, the derivative of the derivative. Probably too much considering, like, the past, wait, let me check, 13 minutes, like, we've only been talking about derivatives for 13 minutes, and I already expect you to know what the derivative of the derivative is, but we'll get into that next video. Optimization problems are classic calculus problems, very applicable to real life. Learn them now, and be good for good for the rest of time. I don't know. Tangent line approximation and Newton's methods, practically the same, but and related rates. And maybe, I don't know, maybe later, some of the stuff that we missed, like implicit differentiation, the mean value theorem, and antiderivatives, aka indefinite integrals. Ooh, that might be the start of a new series. But until then, the next video is going to hopefully be coming soon. No guarantees. Maybe later, maybe not. I don't know. This video is to be continued. And yeah, until then, I will see you next time. Bye for now.